Okay, hello everybody. Thanks for having me here today. I'm going to talk about binary interactions, and in particular binary interactions that make dust. And the connection with cool stars will come. So I'll first, of course, tell you what this common envelope is. Not everybody knows. And why it's important in general, not just to cool stars, but to the populations of various objects and transients. Simulations is what I do, so I'll talk about those. And as all good simulation people, I just don't trust and don't believe my simulations, and none of you should if you're a theorist, okay? So I'll tell you also what I mistrust. We'll talk a little bit about observations as well, and how we can constrain the simulations and be useful. And in particular, yes, this synergy between observation and simulations, everybody knows, right, that we have to do that, but not many people do it. So I'll show you what we've been doing in this regard. To just get you going, I will show you a movie by Miguel, who's just finished his PhD with me. It just gives you an idea what the common envelope interaction looks like. I put music to these movies because I think it's great. Some of you will have seen this already. My students tell me to tell you that it's not their fault, okay? So it's my fault. Okay, let's see.
Like a snowball down the mountain, or a carnival, like a carousel in time, running rings around the moon, like a flow with hands for sweeping past the minutes through time, like a world is like an apple, softly it's fading, like a fledgling heart, with no nearby, like a tunnel for a tunnel of its own, down the hollow cavern. The sun has never shone like a door that keeps revolving in a heart of in your head. Why did summer go so quick? Was it something that you said? Lovers walk along the shore.
So what you've just seen is not a particularly scientific rendering of a 1.1 million particle SPH simulations with phantom from Daniel Price here at Monash. The simulations have about an AGB star, about 2 solar masses, and a 0.6 solar mass point mass companion. And I have a bunch of other characteristics that I'll talk about in a second. Now, to give you slightly more the idea, can I go forward? There. Okay, oh, too much. Okay, back one. Oh, back forward one. Okay, so to give you a slightly more technical idea of what we're doing here and the challenge, you have these phases of stellar evolutions where you have a very, very long secular nuclear time scale phase of detached binary. And eventually when the star expands, and for me, they're into the RGB or AGB, they start transferring mass to the companion as they go through Rochelov overflow. Now, a bunch of things can happen here, and there's a lot of controversy as to just when you go from a stable conservative mass transfer to potentially unstable non-conservative. But let's just say for a second, with giants, convective giants go through Rochelov overflow, the mass transfer tends to be unstable and non-conservative. And you go through this phase where the companion cannot accrete, expands, fills its own Rochelov. I even have is it the top? Not the middle. Okay. They end up with mass loss through L2 and L3. This shrinks the orbit, and then eventually a new force takes over, which is gravitational friction, that leads to the companion in spiraling through the envelope of the giant, and eventually giving some of this orbital energy to the envelope. Two things can happen. One is that you have a surviving binary with an ejected envelope, or simplistically put, the two cannot eject the envelope and merge into one. Now, the challenge of the simulations is that you have an enormous range of scales, both of time and space. So you basically have to resolve the orbit, which could be, AU size. You have to resolve potentially, we actually don't, but resolve the core of a giant, which, as you know, is a pea in a football field. It's like a white dwarf inside a very, very large star. You have to resolve timescales of orbital timescales, which could be years. And of course, you then have to resolve the final stages, which have orbital periods of hours. So it's actually a huge challenge. And for that reason, it's not been tackled very successfully for a long time. But before I tell you a little bit more about the tackling it, let me tell you why we care about this interaction. So it was this guy, Bogdan Paczynski, who basically, to explain cataclysmic variables, said, well, we have a main sequence star and a white dwarf in orbits of, let's call it a day, but it's less than a day, hours. This guy, the white dwarf, used to be a lot bigger than the orbit is today in the past. So we use, huge star. So clearly this implies an in-spiral of some sort. Now, it turns out this is not the only object that a common envelope can explain. About 1 in 5 of all planetary nebula central stars, post-common envelope objects, type 1a supernovae, whether they are single or double degenerates, have gone through 1 or possibly even 2 common envelopes, and so on and so forth. Of course, the very big interest today is in double neutron stars, potentially with double black holes, although those may have different origins, but double neutron stars have also evolved through common envelope stages. So people who try to predict, say, supernova rates or the rates of gravitational wave emitters, neutron star binary mergers, have to understand how the common envelope shrinks the orbit to give you the compact binary, then go ahead and do the type 1a supernova or the merger. And so in order to do that, you really need to understand that shrinkage. What happens in this common envelope? And this is where simulations can help. So the simulations, for the longest time, I started simulating this stuff in the early 2000s, and there hadn't been a lot around at the time. There was a bunch of simulations in the early days. But ultimately, I thought, well, if you take a binary and you have the giant star with its parameters for primary mass, secondary mass, core mass, distance, radius, etc., what we want to understand is how the common envelope in this system gives you that system, the compact binary with a final separation and a bunch of other parameters. And this, if I could do this in simulations and understand how you go from this to this in a common envelope, I can get a nice function, right? Or some way to parameterize the common envelope itself. And if I can give this to population synthesis people, then they can make these predictions of rates much, much easier. I even had a grant in 2006 from the NSF to do just that. And of course, when we started simulating, we realized just how hard a problem it is and how many uncertainties there are. And I wanted to give you an idea of that by just telling you, so these two simulations, there was one simulation in the late 90s and a bunch of simulation in the 80s particularly, with 2 separate codes. This was an SPH code, this was a grid code. They were the only simulations around when I started thinking about this. And in fact, I worked with Ron Tam, and we got the grant together in order to just do this nice parameterization, which everybody wanted and clearly was easy to do, right? And of course, it was so hard and there were so many problems that my first PhD student, Jean-Claude Passy, who calculated the first new generation common envelope simulations, in his thesis defense, the examiner said, Jean-Claude, have you solved the problem? He said, no, I've not solved the problem, but I've created one. And indeed he had. And look, he created a problem big enough that all these other groups emerged to solve that problem. And this has actually generated a bit of a community in common envelope simulations, which is fantastic because, as I said, don't trust your codes. But when so many people start calculating things together and start agreeing on a few things, then maybe you give it some more trust. So what can we determine with the simulations? Well, here is your separation and bound mass. So this is your in spiral. So we're starting to believe our final separations. This is your bound mass. So the bound mass goes down because you're unbinding the envelope. The 2 curves are just 2 different ways of calculating bound mass. So we started to understand ejected mass. Mass loss rates, this will come back for a cool star story. Yes, we can calculate that. Obviously, they're huge if you calculate the total mass loss rate, the 10 years, about 1 solar mass is 0.1, so it's pretty high. But you can also calculate the mass loss rates towards the end, which are probably more telling for observations. Ejected mass, critical mass ratio to get a merger or a binary. So all these things, I would say, they've been now hammered by many codes, and we're starting to really have some communal understanding that we're okay with these. These ones, on the other hand, I would say I've just done the first ab initio, let's call it almost ab initio dust simulations. So they're perhaps a little bit more, well, a lot more uncertain. So from now on, take everything with a pinch of salt. The dust mass that gets produced in these interactions, the photospheric radius, so how much this thing grows and what do you see of it. Okay, so we basically carried out 2 simulations with a 2 and a 4 solar mass AGB stars. These are pulsating AGB stars on the 4 thermal pulse. Secondary is 0.6. We decided a C2O ratio 2.5 because we wanted to do carbon dust, because as you well know, carbon dust is easier to deal with. And we have a carbon dust module in Phantom right now. We are generating an oxygen dust module as we speak. The C2O ratio is high. I've taken this paper by Paolo Ventura. There's a couple of models, including Amanda's and Aton. And we kind of, we just decided, let's go for the highest we can to see an effect. Imagine you take a carbon to oxygen ratio of 1.1, nothing happens. And you say, oh, now I have to calculate another simulation with a higher ratio. So start with high. Remember, the simulations take months, okay? So it's not easy to just do one. So carbon dust, no dust destruction. This is a possible problem, and dust driving. So this was why I was interested. Can dust help unbind the envelope, which is one of the important things in common envelope? So this work was done by my postdoc, Luis Bermudez. And the first thing we took a look at for the 2 simulation, the 2 and the 4 solar mass simulations, this is in spiral, so the reduction of the orbital separation. This is the unbinding of gas. The orange and blue lines are with dust and without dust, and you can tell there's not a great deal of difference. And so the first interesting result was a no result, was that there wasn't a great deal of driving at the hands of the dust that forms. And I'll show you in a second, there's a lot of dust that forms. The reason for that is that dust forms in material that's already unbound by other energy sources. So, it helps push a little bit, but definitely not unbind the material that's already unbound. So this is true for these 2 simulations. If there's something I've learned in common envelope, is every time you change parameters a little bit, things change. So you can't make global conclusions from local simulation. Now, this is just going to show you the opacity in the 2 orbital plane and perpendicular planes. So you see a little bit about where the dust is forming. So the opacity grows when the dust grains condense. And then you see in this particular simulation, you have an interesting axial symmetry. In the other one, you didn't, because the mass ratio was different. So this is just to give you an idea of where the dust is. You look at the scale here, it's about 1,000 AU, right? So there's about 1,000 AU, not Arsen. Okay. So this is the dust mass. It obviously starts at 0 and then it grows and it goes to the theoretical maximum. That is basically if you take all your carbon and you lock part of the carbon up in CO, and then whatever's left gives you the dust grains, the monomers and the grains. So this basically is fast. Look at the time scale. These are decades. So in decades, we make very efficient dust. Now, as I said, take this with a pinch of salt because this is the first simulation where dust has been nucleated. We also have some simulations in post-processing that were published earlier by my ex-student Roberto Iaconi. There too, we see a efficient dust formation, but that was in post-processing. Now, we just need a few more people, a few more groups to do the same, to just start really corroborating each other's results. So explosive dust formation, think of luminous blue variables. These are just a very fast ejecta that give you a lot of dust in a short time. So other things we can get out of the simulations are the size distribution of the dust grains. So this is radius away from the core. This is the size of the dust, and the color is when the dust was formed. Light is dust that formed early in the simulation, and dark is just formed right towards the end of the simulation. So you see that you get up to a micron or so for different moments in time, but ultimately with this, you can calculate things like this. Now, this is super preliminary. This was Christoph here at Monash using MC-FOST and doing a very quick radiation transport. And the big blobs are not octagonal planets. They are just artifacts, but we're working on this as we speak. The idea is just that we can really start understanding a little bit more about what we have. What we have done, so you can also start understanding the kinematics of your material. The photosphere, as I'm about to show you, is about here, and so you can tell the photospheric, the photospheric expansion. So if you had a gas and you could do spectra, you could see that velocity. And Chun Liang, who's my youngest PhD student, started a project to get the light out of these simulations. And the way we're doing it, so the first approximation is the simplest you can think. You take your simulation, which is a big 3D hodgepodge of gas and dust. You look from the outside, you integrate in, and you integrate by, of course, doing your optical depth, which is your opacity, the density, and of course, the length you integrate along. The two colors are two rays. One is going in through your equator, one is going in through the pole, and they're quite similar. The high opacity, so this is just opacity that we get from the dust formation. This is the dust opacity here, very high. There's a lot of dust on the outside. The reason the opacity drops here is because that's not dusty, and it's neutral gas, so neutral hydrogen is transparent. And then you go up as electron scattering opacity takes over, and you have high opacity again. So think of this as this huge cloud of dust. It's really fast and it's expanding quite quickly, and you're now flying in. So this, you see a wall of dust, then you go through the wall of dust and you see a clearing. And then down there, you see the hot photosphere. So there's this is the clearing here. Now, you integrate that, you get the optical depth. And when the optical depth is approximately unity, you call that the photosphere. And then you look at the temperature of the photosphere, and you can do a quick radiation transport or black body approximation, whatever you want, to get the light for that particular ray. Now, what I have here is you take your simulation, you take lots of rays going in all directions like a porcupine. And in each ray, you mark where the photosphere is, and then you color code the temperature. So what you're seeing here is basically the ball, that is the temperature. Blue means it's relatively hot. And then I'm about to show you what happens. And you'll see the dust cloud forming now, right? So this is your dust. It becomes your photosphere. And now look at the scale is changing. So this thing is growing, and it's just this ball of dust, which is cooling and expanding. So we can calculate now the temperature, and we can get the light. Now, before I do that, this is a summary of the average size of your dust ball, basically. So you see how big it gets, 100 AU here. So there's a fast growth at the beginning, and then a slow growth as your dust ball continues to expand. And this one is without dust. So that was just a quick comparison to see what the dust does to the optical surface, or the surface of last scattering. So I said that the next thing you do, you look at the temperature of the photosphere in order to obtain the light. So this is the temperature evolution, the average temperature evolution for the two dusty simulations we did. And as you can see, it just drops and cools. These ones was without dust. Now, the issue here, which is the big, it's not even an elephant in the room, it's a very loud elephant, is that because at the very beginning of the simulation, you have very steep temperature gradients at the photosphere. And of course, all of those of you who use this pH know that your resolution decreases when you have low density. You have low density photosphere with very poor resolution and steep temperature gradients. So you know what that means. It means that you have a relatively large error bar on temperature, which will translate in an even larger error bar on luminosity. So it turns out that when you have steep temperature gradients, you really have to be careful, and potentially you can't do the light. The error bar is just too large. So I'll come back to that issue. What this is basically giving you an idea of the photospheric size on the orbital plane and on the perpendicular plane for the same simulation. This is a 2 solar mass. And one thing I would point out is that the dust photosphere establishes itself after 3 to 5 years when dust starts forming. Before that, if you were to look at the object, you'd see the gas. And of course, it grows to the sizes that we talked about. So these numbers are the first numbers that are not only, well, we'll see how we refine these values as we keep going with the simulations, but ultimately these are the values we want because, as I'll show in a second, they are directly comparable with observations. So this is now what the thing would look like if you were close. Remember those opacities I showed you, those are Planck mean opacity, so they're not wavelength dependent. So this is a gray situation at the moment. Now, what you're about to see is we're moving out, right? So the scale is increasing because the object is increasing dramatically. One is looked at from the side, one is looked at from the top. So the side is on the right, the top is on the left, and the time is moving forward towards 44 years, which is the end of the simulation. So this is how the intensity is distributed on what you can see on that photosphere that we're talking about with some interesting features. This is the lower of the two, lower mass of the two simulations, which has more features. The other one is a lot more round because it has a lower mass ratio. So if you integrate all of this into one point of light, you get a light curve. So these are both simulations, the 2 and the 4 solar mass, and they're for a viewport looking at the pole and one looking at the side. Perfect. So the problem I told you is that early on, when you're looking only at the gas photosphere, and particularly when temperature gradients are steep at the photosphere, I don't believe you can believe it at all. So because I'm conservative, I'm going to tell you to mask off up to 15 years. Possibly it's only the first 5 that are really problematic. But we haven't done the exercise of actually looking in detail. That's what Chunyang's doing at the moment. But later on, you have this big thing. The temperature gradients are now much shallower. And so you can start believing your error bars probably here will not be devastating as it would be in the earlier part. Now, this is clearly not a direct comparison. This is an Ogle light curve. I was talking to Tomek Kaminsky at the conference a couple of weeks ago, and he was telling me that they do see things that are really odd transients that are dimming and becoming, in this case, optically invisible to Ogle. Obviously, this is not a particularly dim magnitude, but if you let it keep going, potentially it's dimming. So is it possible that some objects are dimming in optical because they're being overcome by dust? The time scale here is a few years. We are looking at dimmings from these dust shells of the order, in time scales which are of the order of decades. So it's not impossible that we could potentially see these in the transient population. Now, observations. So obviously the observations I told you about before that we're trying to explain are one thing, but then I'm looking for observations that can constrain the actual simulations that I'm doing today. So all of you probably recognize this as the AGB, post-AGB and white dwarf cooling track. We have AGB stars, we have pre-PN, which are post-AGB nebulae that are not yet ionized and eventually you ionize. I picked these 3 objects because all of them had rings, which are potential signatures of binary motion, because I like binaries. So there are, starting with the AGB, there are 2 types of objects at least that may be things caught in some kind of aftermath of common envelope. The water fountain objects are oxygen-rich objects for which we know, we presume are low-mass AGB stars. This is from this paper here. Bipolar outflows, this is an artist's rendition, coming out about hundreds of kilometers per second, incredibly large mass loss rates, and large photospheric radii, with timescales of existence of this phase of the order 200 years. All of these parameters are ballpark okay for being post-common envelope objects, including the numbers we get, as in how many of these objects we get, given that they don't live very long. The other one is from a paper of Flavia, these extreme carbon stars that she could not model the dust production for. So these objects down here, they are very high optical depth at 10 microns, and they come probably from low mass progenitors. So these low mass progenitors just don't have enough mass to make that much dust, to obscure them that much. So these things could potentially have been obscured, have more dust created than you would in a single star scenario. So these these are these objects here, and they're always extreme enough that it's very hard to get them with single tracks. I was actually visiting Flavia a few weeks ago in Rome, and we're trying to figure out how many of these objects do you have, and we came up with a few percent at the moment. We just have to refine this. But the numbers don't seem too bad when it comes to how many you have of these and how long this post-common envelope dusty phase would last. We look at pre-PN. Pre-PN are amazing because we think that pre-PN, meaning they'll become PN, but actually they're very specific class of objects where the powers and momenta in this collimated outflows can only be explained for most objects with a binary merger. There is reasons for that. I don't have a great deal of time left, but ultimately this paper by Blackman and Lucchini shows that the only way to make these as measured is to get the type of power you get in a disk that forms around the core, the post-AGB stars, from a basically shredded companion. So if this is the case, then these are post-common envelope mergers, then all these nice jet features are actually fantastic constraints for my simulations. And finally, the planetary nebulae. Many of you will have heard that the old scenario where the bipolar nebulae were shaped by magnetic fields and rotation was shown in 2006 and later in 2014 by the original guy himself. Basically, that the problem is that when you make a lot of mass loss, like in AGB stars, and you have magnetic fields in there, magnetic fields are frozen, and they're just basically like the ballerina putting out their arms, and the rotation slows down, and the rotation is basically the engine behind the magnetic field. So the magnetic field quenches in mass-losing AGB stars. So it cannot be the mechanism that creates your bipolar nebula unless the angular momentum can be resupplied by a companion. If so, then you can get the magnetic fields and the whole thing works again, but you need a companion. So we've been looking for binaries in the middle of planetary nebula for a long time. Many groups have done that. And the reason we do is because we want to understand this final separation. Remember, post-common envelope separation is very important for population synthesis, and we want to constrain it. So we use central stars of planetary nebulae. And about one planetary nebula in 5, so one planetary nebula in 5 as a post-common envelope binary. This is a lower limit. This is the ones we can find. There's lots of reason not to find them. So this is basically 20%, right? Of all planetary nebula are these. So it's actually quite a large fraction of this specific interaction. Now, we compare, this is just one of many plots in this paper, comparing final separations with a binary mass ratio, so a secondary over primary. The little dots are the observations, and the big dots with big color dots are all these simulations. And we're starting to, this is actually lots of complexity in here, but we're starting to make these comparisons, right? The real one-to-one comparisons where we're trying to constrain the simulations with actual direct objects, which has been really not happening until relatively recently. And finally, of course, the new kid in town is transients. This is one that's probably 10 already are analyzed with this level of precision, and there's already hundreds of luminous red nova transients that are also to be some kind of common envelope merger, or maybe not merger, sort of binary emerger. And we can, from things like that and precursor photometry, find the mass of the progenitor, the radius of the progenitor, period, the secondary mass, and the photospheric radius at a certain time after peak. Now, as you can see here, we got a couple of months only. What I need is 40 years, right, to see the full evolution of the photosphere. So we're in the phase now. If you've seen the transient outburst, we kind of have to wait a little longer to see the next phase. But we do have hope in all surveys to find this, or even just seeing things for which the outburst was not found and only the fading is seen. So this is incredible. Photospheric radius, ejected mass, ejected velocity, these are all comparable with simulation. So we are really starting a new era of, I would call it one-to-one comparisons. So this is my last slide, just to say, I mean, this might not be so exciting for you, but it's very exciting for me because we've been doing simulations pretty blind, but now we are really starting to look at actual numbers coming from the PN, from the pre-PN, from the extreme AGB stars, and this, the dynamical phase of the common envelope. We have all these luminous red nova transients, of which there are more and more and more every day, that can constrain us extremely effectively. The shaded brown is the area where we do simulations. So this is a primary mass, progenitor's mass. So we have very little simulations at this time just because they take so long, right? But ultimately, many of these parameters for things that are today many, many years after common envelope can feed back into the common envelope itself and help us constrain. So I think that this is very exciting. I am always encouraging my simulation colleagues to bring observations back into the mix. That tends not to happen very readily, but hopefully it will happen more and more. So the take-home message is global 3D hydro simulations have come a long way. We can almost believe some things now, particularly with the dust. This is very much new, but I think it'll take on very effectively. Their direct constraints are cool stars like AGB and post-AGBs, and of course, hottest stars like central stars or PN. Direct, I mean, constraining the simulations. Once we believe the simulations, these numbers will be projected forward, looking at rates of supernova 1A explosions, looking at merger rates, and it'll be really important in that case. But those observations don't constrain us. We're trying to explain them with the simulations. And finally, pop synthesis will be made to make those predictions once we have a better set of more trustworthy simulations. And that's it. Thank you very much.
Hi, Orsola. Thanks for the very nice talk. I have a question about your explosive dust forming model, because the C/O ratio is quite large, as well as not having any dust destruction, but your companion is stellar, right?
The companion is stellar?
It's a star.
Yes, it's a star. So the companion, the way I think of it, is low mass main sequence stars.
Right.
They could be wide dwarfs, but low mass main sequence stars for the simple ones, we see plenty of observations that tell us that they exist.
Yeah, of course.
And in terms of destruction, shocks are there, and they can destroy dust, as you know.
Yeah.
However, interestingly, for stellar mass companions, the motion, the orbital motion is mildly supersonic and then becomes subsonic. So there's not a great deal of shocks.
Yeah.
But, that's certainly something.
I'm just asking because from my chemical models of a close-by companion, we do find that it can affect the chemistry quite a bit. So maybe if you destroyed your seed or your precursor molecule,
yes,
so that could have a...
But remember, you have things in the wind, right, that go on for a very long time.
Fair enough.
Where this is a quick passage, right? So the thing itself eventually goes to the core, and it's a little binary then in the core, and your dust is really far out. And then the shocks remain as a question mark, but I would say direct emphasis of the companion, direct influence of the companion.
All right, okay, thank you.
So that luminous red nova that you showed, and it's a post-merger object. What was the evolutionary phase of the primary when it merged?
So when it's like, as you know, in order to know that, you need to do precursor stuff, and it's not always there. When it's available, they seem to be subgiants, or, a lot of these luminous red nova, because of the statistics, are far away, and hence they're more massive. So we have fewer of, which is why I showed that one, because it's relatively low mass. But when they're more massive, they tend to be right as they become, There's also a question, probably they're brighter when they're from subgiants than when they're from much larger objects. So that's potentially a bias that you see them at that stage. And
hi, Orsola, thanks. This slide that you've left it on right now, indeed, 1 in 5 PN post-common envelope binaries. You said this is a lower limit. So what percentage do you think might be the real limit, or,
It's a really good question. So since I've been doing this for a very long time, I have a very strong opinion on this, but it is absolutely uncorroborated by facts. So I think, given what I've looked at in terms, I've also looked for binaries with infrared excess, with radial velocity, that we've been finding a few at months periods. We're starting now to see, using this method, multiple tens of days. So I think that post-common envelope of this kind, probably 30% instead of 20. So not 100, no way, right? And so there's probably just a lot of nebulae that are from wider binaries, months periods, years, and those are really, really hard to find a companion for.
This may be a naive question, but what if the companion is also an AGB star? Does it happen, or it has not? No object has been observed to
So
be like.
2 AGB stars.
Yeah.
Well, for that to be the case, the fine tuning in initial mass is extraordinary because, as
Yeah.
you know, it takes so little time to go up the AGB.
Yeah.
So then you can into the very interesting topic of equal mass binaries, right? Are they, is there such a system that gives you a predominance of equal mass binaries at
Sure.
formation?
Yeah.
But then it really has to be within 3%. It's like a really
Yeah.
to be at that.
But is there any observed object that could fit that scenario, or
I don't know of
you don't-
any.
Okay,
Would be very
it will be
interesting.
very rare. Okay, thanks.